So just a zoom in, if you will, on the residential wiring. Again, after the step down transformer, and you'll see these. These are these gray cylindrical cans that are attached to the light poles as you drive down the road. Every few poles as you're driving down the road, next time you drive along, look up and you'll see these gray cans on the side of the poles, right? And those gray cans are the transformers. And so one of those transformers steps down and typically feeds several houses in the vicinity. So you don't see them at every single house or at every single pole. Why? Because they're expensive, right? And so they transform down and then they distribute. Again, the 240, right, the black from the hot and the red gives you the other end of the hot with the neutral in the middle, or the which is attached to ground. And that's another thing. The ground is actually attached to the neutral because you want to provide a path, a safe return path. So at the very least, you want to make sure your ground wire has a safe way to get rid of the current. Where does it go? Into the ground. So the ground wire, actually, you'll see a couple of different things are used but the main way is that outside of your house, when the power line comes down, they actually drive a spike into the ground. And the ground has got moisture in it, and it's got minerals in it. It's actually somewhat conductive. So they drive a big metal stake way down into the ground, 5 to 6 feet at least usually, and then they just attach a great big fat copper wire to that. And it just provides an emergency place for extra electrons to go, right? So that all that current can get away if it can't, for some reason, get back into the system. Right? So again, that's a safety. Inside of your power distribution panel, the neutral and the ground are also often typically tied together, right? So you'll see the neutral wire come in and be bolted to the ground, or the ground wire be bolted to the neutral. And then there's oftentimes a secondary. They'll run maybe a ground wire over to your water main. Why? Because that big piece of pipe is copper and full of water, which also conducts electricity and is buried underground. So it gives another emergency return where they can safely dissipate electric current. Right? So, those again are safety issues. The system will run just fine without the ground wire, but you don't have that added layer of protection that if you accidentally, suddenly if you became, why is that important? Because for safety's sake, right, if I'm standing in a puddle of water in my bathroom and I'm wet because I just got out of the shower, right, and I grab my hairdryer and my hairdryer has quite a bit of resistance in it, and maybe there's a short through one of the pieces of insulation because my hairdryer is old and I didn't want to buy a new one, right? And so now my wet body and the puddle of water I'm standing in connect me to a lower voltage on the ground than the hairdryer would have to push, right? I'm an easier path. I'm a lower impedance, lower resistance to the low voltage of ground than the wire going all the way back to the distribution panel in my house. So the electricity, the current, right? What do we know? Current follows the path of least resistance, so it goes through me instead. So by providing that additional ground wire, we provide another spot where hopefully if there's a short or a problem, I can still fry myself if I try hard, right? The ground wire helps me to make sure that I'm not the path of least resistance, right? Similarly, there are other safety things like ground fault interrupt connectors, right? Or GFCIs, ground fault connect interrupts or whatever, that they work by a very similar principle. They measure, in fact, the current that comes out of this wire and the current that returns. And as long as those are equal, then all is well. But if there's ever something unequal, meaning some current came in this way and then went down through a person, probably, maybe, into ground, that's bad, right? So the current coming out does not equal the current going back, then it's essentially a second switch right there in that middle. And that's those boxes you see in your bathroom that have the little electric boxes with a button on them and a little light, right? And there's like a test and a reset button if you ever look closely at them, right? Really, if you push the test button, it momentarily allows the current to flow to ground, And so it trips its little circuit breaker inside, opens a switch, cutting off this hot line, and then protecting you. And that has to happen in less than 6 milliseconds, right, to keep you from hooking yourself. In fact, I did a research project with one of our students a couple of years ago. He developed a new type of sensing system that would actually detect if a person plugged themselves into the hots, or to the hot and the neutral. So you weren't a path to ground, you were actually the circuit, you were the light bulb, right? A ground fault can't detect that. We came up with a circuit that does, right? And that will actually cut you off from that as well. So, you know, again, because safety is of paramount importance. Right? Electricity can kill you dead really fast. So it doesn't take very much. It takes about 100 milliamps of current through your heart, and you'll be toast. Which doesn't seem like a lot when you figure we're talking about tens of amps coming out of these things. But at 120 volts, and we're like a couple of mega ohms. So normally there's not very much current flowing through us, right? A couple of microamps or so at the most. But 120 volts is enough to give you a good shock, and then if you suddenly become more conductive, more current's going to flow, right? And it can be a serious danger. This is what we already were talking about before, that, for example, when you bring in to a room, you'll have, you know, multiple lamp sockets or actually multiple, you know, either lamps overhead or, you know, receptacles on the wall, you know, that you can connect to off of a single circuit, right? And so essentially what does that mean has happened with each of these lights, each of these receptacles? They're all connected in parallel. Right? So essentially you have a cable that runs around the room carrying both the hot and the neutral, right? All the way around the room. Anywhere you tie into a receptacle, you may cut that cable completely and wire that into the receptacle, but then if you look at the receptacles, they also have an out. So there's a master connection and a slave connection. Do you guys remember that from last semester? I know it's been a long time. In the lab, those were big yellow panels. You remember the one you did at like the beginning of last semester? Well, I know, Mickey, you weren't here, Brian, you weren't here, but, you know, so if you remember that big yellow panel, when you wired up the receptacle, there was a master connection and a slave connection. So the master is where the wire comes in, and then the slave is where you can connect to continue the parallel connection, right? And those are actually connected by a piece of metal inside. Right? And then those, so that can continue on, so you can connect another lamp or another receptacle down below. And the lamps, you turn off the lamps by inserting a switch in the wire.